Hello to all of you. This is Dr. Dhaval Maheta, and today we are going to discuss a regression matrix of machine learning algorithms. The performance of machine learning algorithms is evaluated with the help of various metrics. This metrics influence how you weigh the importance of different characteristics in the results and your ultimate choice of which algorithm to choose. Various different algorithm evaluation metrics are demonstrated for both classification and regression type machine learning problems. The dataset which we have considered here are downloaded from UCI machine learning repository. For classification metrics, which we have seen in my earlier video, we have used PIMA Indian diabetes dataset. In this case, it is a classification problem where all the input variables are numeric and the target variable is in binary. In this video, we are going to discuss Boston house price dataset, which is a regression problem in which all the input variables are numeric and the target variable is also numeric. A tenfold cross-validation test harness is used to demonstrate each matrix because this is the most likely scenario you will use when employing different algorithm evaluation metrics. Some of the common regression metrics are mean absolute error, mean square error, and R square. Mean absolute error is a sum of the absolute differences between the predictions and actual values. It gives us an idea how wrong the predictions were. The measures gives an idea of the magnitude of the error but no idea of the direction. Example, either it is overpriced or underpriced. Or rather, we can say it is overpredicted or underpredicted. Now, let's see how we can do this in Jupyter Notebook. Import pandas from sklearn import model underscore selection from sklearn.linear underscore model import linear regression. We'll specify the URL where the dataset is located. Names of the variables are there. There are 13 variables. Data frame is equal to pandas.read underscore CSV. We'll specify the URL. Delimit white space is equal to true. So all the white space is considered, and on that basis, we are classifying the data. Names is equal to names. Array is equal to data frame dot values. X is equal to array colon comma 0 is to 30. Y is equal to array colon comma 30. K fold is equal to model underscore selection dot k fold. Number of splits we are considering 10. Seed we are specifying 7, and shuffling is to be done true. Model is considering a linear regression. Scoring here will be negative mean absolute error. Results is equal to model underscore selection dot cross validation score model x y. Cross validation is according to the k fold. Scoring we are using negative mean absolute error. Print mean absolute error. And when we will run this, we will get the answer, which is minus 3.387. The idealistic value is nearer to 0. It means that if it is 0, there is no prediction error. Here it is having minus 3. The next is MSE, that is mean square error. The mean square error is much likely the mean absolute error in that it provides a gross idea of the magnitude of error. Taking the square root of the mean squared error converts the unit back to the original units of the output variable and can be meaningful for description and presentation. This is also called as a root mean squared error. Let's see how we can do this in Jupyter Notebook. Import pandas from sklearn import model selection. From sklearn.linear underscore model import linear regression. We'll specify the same URL which we had seen previously. Then we specify the variable names. 13 variables are there. Here medv, which is the last variable, is a continuous variable, which is a target variable, and that's the reason we are using regression matrix here. Data frame we are specifying pandas.read underscore CSV. We specify the URL from where the data has to be fetched. Array is equal to data frame dot values. X array, Y array. K fold is equal to model selection dot k fold. Number of splits 10. Random state 7. Shuffle is true. Model is equal to linear regression. Now this time scoring we will be considering as a negative mean squared error. Results model selection dot cross validation score, model, which will come from here, x from here, y from here, and CV is scaffold, scoring is equal to scoring, which is based on negative mean squared error. Print MSC. So what I get is a mean squared error. Now you take the absolute value of this, and if you take the square root, you will get a root mean squared error. Next comes is a R square matrix, also known as the explanatory power of the model. The R square metric provides an indication of the goodness of fit of a set of predictions to the actual values. In statistical literature, this measure is called the coefficient of determination. This is a value between 0 and 1 for no fit and perfect fit respectively. So the idealistic situation is 1. Let us see how we can do this in Jupyter Notebook. Import pandas from sklearn, import model selection from sklearn.linear underscore model, import linear regression. We specify again the same URL. Names are there. Data frame is equal to pandas.read underscore CSV. Array is equal to data frame dot values. X is equal to array. Y is equal to array. K-fold. Same. It is repetition. Model is equal to linear regression. Basically, all the previous commands are repeated. Now, you should take care in scoring. Here, we'll say R square. Results is equal to model underscore selection cross validation score model X, Y. CV is cross validation according to the K-fold. This K-fold. Scoring is equal to scoring, that is the R square we want. Print R square. We got 0.718. Anything which is above 0.6 is considered to be quite good. It means that our model is able to explain, or rather, all our independent variables are able to explain 71% variance of the dependent variable, which is considered to be quite good. All these codes are given in the book Machine Learning Mastery with Python, written by Jason Brownlee. For more videos on machine learning using Python, kindly subscribe to my channel. You can follow me on LinkedIn and Twitter. Please refer my playlist in which I have already uploaded many videos of machine learning using Python. Please don't forget to press the like button. Thank you.